people who limed, which were often the people who grew canola, they would typically realise that they're on an acid soil, and then the rule of thumb might have been to either just apply a blanket rate of lime at, say, a tonne to the acre or 2.5 tonnes to the hectare, and just think that we're doing a good enough job. The people who soil sampled, they would have typically taken a standard soil sample, which is a 0 to 10 centimetre increment, usually just at the surface. They'd have got a pH value on their soil test result, and if the soil test result came back at less than probably 5, they'd have thought that it's time to lime, and in which case they'd probably just put on their tonne to the acre of lime. The research that has prompted the most recent changes in our recommendation has been a series of surveys that have sort of identified that we've underestimated the true extent of acidity, and that has, made us aware that we actually haven't been managing soil acidity well enough. We've had to make some changes, and so changing the way that we sample our soil so that we're actually aware of how the extent of acidity has been the first step, but also understanding what our target pH level is, so what our target lime rate might have been in order to address the acidity on a given paddock. The rule of thumb of a tonne to the acre, whilst that might have been the appropriate rate in some paddocks, it certainly isn't universal across soil types, across rainfall environments and across production systems. So very much more targeting how much lime that we need to put on in order to address the acidity that's in a given paddock. Traditionally, 20 years ago, we would have applied lime once the pH got below 5, and the rationale for that was because, well, below pH 5, we would expect that aluminium toxicity might start to constrain plant growth, so that was reasonable. However, we now know that pH 5 is probably not enough, and so the new trigger is actually pH 5.5. The reason for that is when we get our soil pH in the surface up to above 5.5, the soil chemistry changes and the lime exists in a different form. It exists in the bicarbonate form. And so what that means is actually when it's in the bicarbonate form, it can actually move down the profile more effectively. So by increasing our pH target at the surface, at the soil surface, we're actually much more effectively able to manage soil pH or soil acidity in those subsurface layers because our alkali can move down the profile. So that means that our new pH target is, let's call it 6, and our new trigger to lime, again, is pH 5.5. Knowing the target pH for rhizobia is important because rhizobia is important in legumes. We have rhizobia and legumes, we have a functioning symbiosis. That's what gets nitrogen back into our soils. The target pH is a bit difficult to answer because it will be different for different species, but by and large, if we adhere to the new liming targets, so if we're liming when our soil test value gets below 5.5 and we're targeting a pH of about 6, most of our legumes shouldn't be constrained. So that should maximise legume production, maximise legume growth, and therefore maximise the amount of nitrogen going back into the soil. Soil pH is a fundamental driver of soil chemistry, okay, and it impacts all sorts of things like nutrient availability. One of the things that I've spent a bit of time on researching is the effect on soil water and more particularly around drought resilience. So liming an acidic soil is an advantage in drought-prone environments because it makes more water available to plants, and that happens through probably 3 mechanisms. In some soils, not all soils, but in some soils, physically liming actually increases the amount of water that goes into the soil, so it can increase infiltration. What is probably the larger driving factor is the ability of plants to pull water out of the soil. So, if we lime and we get increased pasture growth because we've limed, we've got bigger plants, bigger pumps, we're actually able to utilise more of the deep soil water, and that's great for production. It's also great for actually mitigating risk of other soil degradation such as dryland salinity. And then the other thing that we're doing is we're addressing the acid soil toxicities. So in New South Wales, a lot of the acid soils are associated with aluminium toxicity, and also manganese toxicity. Aluminium toxicity is considered a toxin of the root, and so that will physically constrain root growth. If you've got a sensitive plant such as lucerne that's growing on an aluminium toxic soil, you will see shorter stunted roots, shorter fatted stunted roots. And so that obviously constrains that plant's ability to explore the soil volume for water and nutrients. Manganese toxicity is a little bit more variable. It doesn't exist in all soils, and it's not uniform throughout the year. It's sporadic, but when it exists and when it constrains plant growth, it can also reduce root growth. Not because of the physical constraint that aluminium provides, but because manganese is a toxin of the shoot, and if the plant is smaller, then the root is smaller, and therefore it can't access the same soil volume. And so the other benefit of ameliorating acid soils is, of course, you've got a greater range of species that can grow. So many species that we rely on, and lucerne's perhaps the best example, but certainly not the only one. They're sensitive to acid soils. They're sensitive to low pH, but to also high levels of aluminium and high levels of manganese. If we are able to ameliorate our acidity and get these species to grow better, we actually have more species options available to us in the farming systems. And that's a real benefit, because that will allow, if a farmer can all of a sudden grow lucerne, where in the old days they couldn't, all of a sudden they've got new options to finish livestock, to fatten lambs. So there's a whole range of system benefits. It's not just about how much biomass you can get off a paddock.